So I have phase A that is connected with the load, and then phase B. So phase A that I can consider that I have connected a generator with this one, and then it is connected. Let us consider it is star connected for the simplicity. So then this one is connected with this line. So this is my A line, this is B line, and the other one is connected with the C line. Okay. And this current is flowing here, IA, and this current is flowing here, IB, and this current is flowing here, IC. Now what is happening is this line is shorted. So you may have connected with a load here. That load has an impedance. Let's consider this one. So this one will be here one load, and this one here will be another load. So this is my ZL, just simple understanding, ZL. Now this point is connected here. So what will happen? This current is initially flowing in this direction. Now I have make it shorted. Now what will happen? Who can tell?
All your current, so the current through your red phase or your A, that's
Yeah, let us draw this fault line with a different color.
so that voltage on
I
A
want to make a fault line, this green one. It should be red one, actually, the fault one, but I have drawn, say, this one is the fault line. Let us write in blue also. So fault line. So this one is connected as a fault line between B and C. Now, what will happen? What is the impedance of this one? ZF, fault impedance.
Probably very low.
Very low, and that's probably zero, right? We might have some value, but we can ignore. That means I have a zero resistance here, and this red one, I have ZL, and this one is also ZL. So what will happen? The IB current may pass directly to this one and may go in this direction. That means my IC it will be changed to minus IB.
Yeah.
Okay, so that what will happen? So if I have a short circuit like this one. Okay.
Yeah.
So this is what we need to understand. We need to, just from this discussion, we need to understand this is what might happen. So similarly, if you have a three-phase fault and if it is connected to the ground from this point, that means this current will be against zero, and that means IB, whatever current, or this current will not be zero. So IB and IC will all go through this one. So I will have IB plus IC will be going to the ground. Okay.
Yeah.
So the fault current will be IB and IC, and this IB and IC is coming from this voltage VC and VA, and that is given by BB divided by ZF, which is tends to 0. That means this current, IB current, will be infinite. Similarly, IC current will be infinite. Okay. So this is the just common understanding we need to have from our discussion from here. And whenever we have the short circuited, what would be the voltage across this load? Across this load. Previously, it was connected with the VB. That means I can consider that this VB voltage can appear across this load. Now, whenever I have short circuit, what would be the voltage across ZL, especially connected with this phase?
Phase voltage.
The voltage is reduced across the load.
What would be that voltage? Reduced, definitely. What we can expect? Because you have only one phase is connected, and that phase voltage will appear across this one, and these 2 points are shorted. So these 2 points with the short, I can expect 0 voltage across these two phase, almost 0 negligible voltage across this phase.
With a fault, with a faulters,
Yeah,
the current's gone high, so the voltage must have dropped away across those two phases.
yeah, that will be very low, right?
Yep.
Yeah. So yeah, so that's what we are expecting from this one. So now, if I have, now let us continue our discussion from here. I want to start our conception to analyze this circuit. I want to understand how we can analyze this circuit. Now, if I, starting from the balanced three-phase system, balanced double L, right? Okay, balanced three-phase system. So whenever we mention balanced three-phase, that means I can draw a circuit, similar circuit, three-phase circuit with having, say, VA voltage connected and we have, let's draw the other way. So we have similar to this one. This is VA, then we have VB, and we have VC. So we can consider this one is connected with my load ZL, and we can have ZB, ZL, another ZL, and we have another ZL. So all the three line is having same impedance of L. So that means VA, we can have the connection of the neutral here. So this will be called balanced. When I will call this one balanced? This one will be called balanced when I will have the same load connected with each other that will give me same current flowing through this line. So I will have IA, IB, and IC are same magnitude. Now with the three-phase system, if you have, so we are talking about the magnitude only, okay? Now, if I draw the phase, do we know what is the phase look like in a three-phase system? Whenever we are considering VA, so in commonly used phasor diagram, we will have VA would be equal to, let's say our typical voltage is three-phase is 415. Okay, so this is the magnitude, and VA magnitude will produce with an angle of 0 degree. Okay, so that means I will have VA, I can represent as 415 with an angle of 0 degree.
Yeah.
Now, what about BB? What about BB?
120.
So it would be the same magnitude, and this is VA. and that means my VB would be in this direction, right?
Yes.
So this is VV, or in the positive sequence. ABC. Let me just take a look of this, because we will come to that one soon. So I don't want to confuse. So I will have another one would be 120. I think this one is fine. So I will have this one will be 415, an angle of 120 degree, right? So that means these two are the same, and then we will have another one is called VC. That would be 415, an angle of, what is the angle?
Minus 120.
Minus
Minus
120.
120 or 240 positive.
Yeah. Okay.
Oh, this one is 240 positive. This one would be actually 120 positive. So this one would be, that's what I was telling, that this one would be positive sequence. Yeah. So it's all right. So this one is the positive sequence. This one is C, but this one would be actually, this one is not 120, right? So I have written wrong here. So this one would be equal to, so we are going, so positive, so angle positive, when we consider angle positive. So this one is the positive angle, right? So this is the positive angle. Now, if I move in this direction, this will be the negative angle. So clockwise is the negative angle,
Yes.
right?
Yeah.
So we have to be very clear. So if I go counterclockwise, that is the positive angle, and clockwise direction, that is the negative angle. Okay. So if I go from here, this angle will be negative, something minus 30, or, and this angle will be positive. Now this one, I am going in the positive direction, that will be 120. And I can move in this direction to 240. So that angle, this angle is actually 240, I can write 240, or the same one I can write 415, an angle of minus 120, because let me write down in color of to so this is 120 and this one is negative, so this is going in this direction. Okay. And this is called the positive sequence, because positive sequence means I will have the first phase, I will have A, and then I will have B, and then I will have C. So if I move in this direction, clockwise direction, then I will find out A, B, C phase. And this is the three-phase system. Similarly, my current, if I draw my current, I can draw the similarly this current, all these three current will be the same. I can take a look of my current. Each of the current will be separated by 120 degree apart. So this is the three-phase system. So if I know one of the voltage, if I somehow know that this voltage is this voltage has a magnitude of 415, then all the other phases, other lines will have the same voltage. So this is the property of the balanced three-phase system. Now, whenever I have the balanced three-phase system, as these magnitude are same for all the three phase, I can simplify this one and do my analysis considering a single phase only. I can consider that my circuit is having only one phase, that is VA connected with the ZL, And if I can find out with this equation, with this single phase, I can calculate my current I, then all the current will be the same, only they will differ from each other by 120 degree. Is that clear?
Yeah.
Is that clear?
Yes.
Okay, so that means if I have a balanced three-phase system, I don't have any problem. I can just simplify this complex circuit with a single phase circuit, that I have only one voltage source connected and one load connected, and do our analysis. And then we can find out my current. And if I know my current is certain value, then I can assume that my other two current in my balanced circuit will have the same magnitude but different angle. The angle will be different. So that is we need to understand this one. Now, the problem with the fault circuit, now you can see that fault circuit, whenever fault happens, that we have started our discussion with, when fault happens, that initially balanced circuit that was designed and working balanced, but you have a fault, and then it is no longer a balanced one. Okay, so it becomes unbalanced circuit. Unsymmetrical fault happens and it becomes unbalanced circuit. Now, whenever you have unbalanced circuit, your calculation become very complicated. You can no longer consider a simple circuit like this one. You cannot proceed your analysis having only single phase. So this one you can do whenever your system is balanced. Balanced system can be represented, can be analyzed using only one phase. So that's what we have done. We have taken only single phase. We can do our analysis. But whenever the fault happens, it is no longer a balance. Now what we can do? We can do that analysis considering unbalanced, then we have to consider all the three phases simultaneously. So this circuit has to be, I cannot simplify this one with a single phase. That means my calculation becomes complicated. But fortunately enough, that with called the symmetrical component, we can represent any faulty circuit that is unbalanced, that can be represented with three balanced system. So that whenever we have three balanced system, we can separate. We separately do analysis for these three balanced system, and then we find out what is actually happening to our actual fault scenario. Am I clear? So let us just share my other device and come back to from there. So I'll go back and we'll open this one. Now, we are talking about this one, that whenever I have a fault condition, I think up to this point is very clear that if I have a fault scenario, I will not have the same current or the same voltage in my system, that my system balance. Can anybody? Are you talking to me or to the class? Okay, so let us continue. I think it's not to our class. So this system, whenever I have a fault happens, unsymmetrical fault we are talking about, that means this balance is uh, the system becomes unbalanced. There is no balance in my system. Previously, it might be working as a balanced system, but when fault happens, then it becomes unbalanced system. That means I might have a scenario that this current, you can see VA, these vectors are not equal. So you can see here, these vectors, I can just use this one, probably that will help. So the vector VA that is showing here, I change these colors. Yeah. So can I change also this to this marker? Probably that will help. Yeah. So this one, let us try. So these vector that was representing my VA, so sorry, this one is not VA, this is a component. So we'll just remove this one. So my system balance has been disrupted. This becomes my one of the phasor VA, and my VB becomes this one, and my BC is becoming this one. So previously it was a balanced system. In balanced system, we should have VA, the length of the VA vector, and BB vector, and VC vector, that should be all equal. So that should be equal. So that is my balanced system. So I will have, this one would be 120 degree, and then this one would be 120 degree. This is negative. So my VA, and this one should be VB, and this one should be VC. So this is my balance system. Now, whenever is system having fault, then my balance, this system is no longer balanced. So I have VA, you can see is long, very long. That means it's a magnitude is larger.
Yeah.
Then you have BB smaller, VC is smaller. So that might has gone through one of the fault condition. We don't know which fault, but it has having some kind of fault. And these three phases are different. That means my system, I cannot represent my system with this a single phase system. So my calculation becomes complicated. So in order to simplify this one, that my three phase that we have discussed, that can be represented with three balance system. So this particular condition, this particular faulty system can be represented with three balance system. So one is called the positive sequence component. So that means I can decompose this system into this positive sequence component, and then negative sequence component, and the zero sequence component. And if I add them together, they will give me this faulty scenario. You can see that positive sequence component is represented by this number 1. So whenever I have 1, that will indicate this is a positive sequence component. So positive sequence, as we have learned, the normal operating system should produce a positive sequence. Then that means I will have BA, and then 120 degree apart, I will have BB, and then another 120 degree apart, I will have BC. So that will produce a positive sequence. So that means this unbalanced system, I will decompose as one of the positive sequence, and then I will decompose the negative sequence. In the negative sequence, you can see that BC and BV has been changed its position. Now I have BA, then C, then B. That means it is just opposite. This one I can consider is clockwise direction is rotating. And this one is rotating, I can consider is the anti-clockwise direction. So the phases can be found in anti-clockwise direction. That's why it is called the negative sequence component. And then the third one is the zero sequence component. The term zero indicates, you can see these three phasors have been the same value. That is good thing. All these three phasors in both positive, negative, and the zero sequence all have the same magnitude. But here, these three quantity has no phase angle. That means this is similar to a DC component. So it does not have any phasor. So that means we have discussed that in the DC, we have only the magnitude, and this is similar to that one. With the zero sequence, that means it does not have any AC component, it is the DC component. And this is zero indicates actually is related to the ground or neutral. It is connected to the neutral. So we will come to that point. So at this point, we can just identify, we can just get the idea that we have an unbalanced system due to fault, due to any of the fault that we have discussed, the system become unbalanced. That means the voltage and the current in the system is no longer equal. So that means this system cannot be analyzed with our knowledge of simple balance system. So in order to simplify that one, what we have done, this is invented, this method is invented and presented by one of the scientists. And they have identified that if I have a scenario like if the system becomes unbalanced, then I can represent the same system with three balanced system. We can imagine that this unbalanced system is produced due to having scenario of three balanced system. One we call positive sequence system, another is the negative sequence system, and third one is the zero sequence system. Okay, so I will have a three separate circuit, and then if I add the combination, the result of these three circuits, that will give me the unbalanced scenario. Is that clear? Did I able to make it clear to you? If you just understand that if I have an unbalanced system, I can decompose into three balanced systems. That would be great. And how we will do that, that we will discuss. That is why we are here, right? We need to understand. First thing is to understand that we can decompose, we can, from the unbalanced system, we can identify three balanced systems, or from three balanced system, we can identify, we can get a unbalanced system. Okay. So we need to understand at this point. Yeah, any question? Great.
Yeah, I'm just having a look. So between the positive sequence components and you can get the well, you get the magnitude of your the magnitude of the voltage is after the fault. So
Yeah.
you can see that. Yeah, you're just
So that
getting those-
that
getting those-
magnitude is, we are considering the positive sequence, that magnitude is different than the fault magnitude,
yeah.
but they will be the same. This will be the balanced system. We can find out something, some relation with
Yeah.
this one, but they will be the same. Now here, just I will come back to our calculation or how we can relate to this one. Just want to show you from this presentation slide that I have this one. Let's say I will take this color as green. So this is my positive sequence, right? This is my positive. I'm taking this green color for the positive sequence. And then I can take this blue one for the negative sequence, and then black one for the zero sequence. And my actual one was this one that I have drawn, VA. And you can see I have three other components. We have added them with together. So I can have, so I will take again the black one. You can identify this is the black part. Okay, and that's coming from here. So this part I have decomposed. Somehow I have found from here this part, and I have made this value VA not. And this is identifying not is indicating this is a component from BA, and this is zero sequence. So this zero indicates this is the zero sequence. Now here you have A2. A2 is always negative sequence. So this is A2 is indicating a negative sequence. And that negative sequence is, sorry, this one I will take the blue one. So I will have this one is this my negative sequence. And then I have the green one, and this is my positive sequence.
Yeah.
So that means you are adding these three, this one, and then you have added this blue one.
Yeah.
And then you have added this black one, and all these has resulted the resulted fault condition vector.
Resultant magnitude of it.
The
Yeah.
resultant vector that we have got. Okay. So this is the relation. So I can, so why we are doing? So as I have mentioned previously, given the introduction, that balance system, analysis of a balance system is much easier. So if you know the balanced component of your unbalanced system, then you can represent with a balanced system, and then we can do the analysis easily fault condition. Otherwise, you have to think about unbalanced system. You have to consider all the three phases simultaneously, and that creates the complication. Okay. So that's why we want to find out the